Now, you've heard me mention Spectre and Meltdown. So let's get a little idea of what those are. Spectre is a class of vulnerabilities in modern CPUs that exploit speculative execution to access sensitive information that should remain inaccessible to attackers. It allows attackers to trick the CPU into executing instructions along a speculative path and then use side channels, such as cache timing, to extract sensitive data. So Spectre's vulnerability type is speculation execution side channel attack. The affected components of Spectre are virtually all modern processors, Intel, AMD, ARM, and others. Spectre was independently discovered by two research teams in 2017. First, Google Project Zero. Jan Horn identified the issue and demonstrated its impact. Second, Paul Kocher and a team, so he, along with other researchers, documented and confirmed the Spectre vulnerabilities. The findings were publicly disclosed on January 3, 2018, after months of responsible disclosure to CPU vendors. Spectre works with branch prediction, where CPUs predict the outcome of branches to execute instructions speculatively, and misdirection. Attackers create a crafted code sequence to exploit branch misprediction, and speculative execution. The CPU speculatively executes instructions that access out-of-bounds or unauthorized memory. And side channel analyses. Though the speculative results are discarded, side effects like cache changes can be analyzed to infer sensitive data. While there have been no widely reported large-scale Spectre attacks, proof-of-concept exploits have been demonstrated by security researchers. Potential attackers could include state-sponsored actors, cybercriminals, and insiders targeting high-value systems. Theoretical victims include any device running an affected CPU. It could be a cloud service provider, it could be enterprises, it could be personal computing devices. So then Meltdown. Meltdown is another speculative execution vulnerability, allowing attackers to bypass the CPU's memory isolation, enabling them to read the entire physical memory of a machine, including kernel and user data. The vulnerability type is speculative execution and out-of-bounds memory access. Affected components are primarily Intel CPUs, some ARM processors, and potentially, but rarely potentially, AMD processors. Meltdown was discovered independently by Google Project Zero. Jan Hornigan played a pivotal role in identifying and analyzing the vulnerability, and then also by Cyberus Technology and Graz University of Technology, where Daniel Gruss and his team conducted additional analyses and confirmation. Public disclosure occurred simultaneously with Spectre on January 3, 2018. So Meltdown works with first out-of-order execution. The CPU speculatively executes instructions that access protected kernel memory, and then illegal access. Though unauthorized, the speculative execution results can affect the CPU cache. And then side channel exploitation. Attackers use cache timing analyses to extract sensitive information from kernel memory. Similar to Spectre, there have been no confirmed large-scale exploits in the wild with Meltdown. However, the feasibility of exploiting Meltdown was proven with proof-of-concept attacks, raising concerns about potential threats to cloud infrastructure and virtualized environments. Meltdown would primarily target systems running Intel CPUs, including cloud service providers, virtual machines sharing physical hardware, and end-user devices running unpatched operating systems. You can take a look at the chart comparing Spectre and Meltdown. Proposed mitigations for Spectre are microcode updates to add speculative execution barriers like LFENCE in x86, software-level fixes like retpo lines, and changes to compilers to prevent speculative code paths. Mitigations proposed for Meltdown: kernel page table isolation, KPTI, to isolate kernel memory, and software patches for operating systems. Both vulnerabilities prompted significant updates to CPUs and software, with trade-offs in performance due to the mitigations. These findings reshaped the approach to speculative execution in CPU design.